the simplest way? What's the most intuitive way to grasp the counterintuitive notion that time slows down when you are watching a clock in motion? So if you're watching a clock in motion, that clock will tick off time ever more slowly. And the best answer to that is the oldest answer to that. There is no newfangled approach that really blows out of the water any of the other attempts to explain this powerful idea of time and its rate of elapsing depending upon your state of motion than the light clock. And the light clock is this very simple but powerful idea where, you know, when you think about clocks, right? I mean, there are many, many ways of thinking about clocks. They're basically devices that allow us to measure the duration between one event and another. And we do that by having a cyclical process. So if the clock is an ordinary old-fashioned clock, the cyclical process is a hand that just sweeps around the face of the dial. That's one kind of cyclical process. There are many such processes, right? In a quartz crystal, it vibrates in a particular cyclical manner. You count the number of vibrations to determine how much time has elapsed. But a light clock, what is it? It's a device that has two mirrors with a ball of light that bounces up and down between the mirrors. And to calculate the amount of time that's gone by, you simply count the number of tick-tocks of the bouncing photon between those mirrors. And let me just give you a little visual of that, if I can bring this up on a screen here. Yeah, so, you know, if you see this clock and you see you got the two mirrors that are facing each other and the ball of light is bouncing up and down between them, and each of those tick-tocks, that is a way of counting the duration, of measuring the amount of time that has elapsed. Now, once you take into mind, into your brain fully, the idea that that clock that you're seeing, it's truly measuring time. It's an unfamiliar clock. You don't see people walking around on planet Earth with a wristwatch. That's a little box that has a photon bouncing up and down between two parallel mirrors. But once you take that notion of time as really being time, right? If you're measuring how much time has elapsed, you simply count the tick-tocks in that photon, then there's an incredibly simple way of concluding that when a clock is in motion, time slows down. And to do that, you simply show two of these clocks and you say, put one, oops, I'm blocking that thing over there, I think. So you put one on the other side of the laboratory. Let me get out of the way here and look at the photon in the moving clock. It has to travel a longer trajectory, a diagonal up and a diagonal down trajectory. Light always travels at the same speed. So if the photon in the moving clock, let me get out of the way here and play it again. If the photon in the moving clock is traveling along a longer trajectory, diagonal up, diagonal down is much longer than the straight up and down of the stationary clock, then look, it will go tick, tock, more slowly than it would in the stationary clock. And that example, I'm gonna get out of the way here so you can see it. That example right there is a beautiful illustration of how time slows down on a moving clock. Constancy of the speed of light and the longer duration of the tick-tocks in the moving clock is, to my mind, the most powerful means of embracing viscerally this notion that time slows down on a moving clock. And there you see the essential new idea of special relativity. That was Einstein's insight, that the speed of light is constant. Whether you're looking at the ball of light in the stationary clock or in the moving clock, the speed at which light travels is the same. 671 million miles per hour, or whatever units you like to use, 300 million meters per second. And so if the light has to travel on a longer trajectory, it's going to tick tock less frequently. Time will slow down on a moving clock. So if you have questions on that, I consider this to be, you should ask him now. I consider this to be among the greatest achievements of the human mind. That little illustration of the bouncing ball of light establishing that time slows down on a moving clock is one of the deepest insights of the human mind. So if you have questions on that, I'd love to entertain them. But that's the basic idea. Now, others ask, as I see some of you are asking, well, okay, that's the effect on time. Is there an effect on space? And there is an effect on space. I don't know how easy it will be for me to show you that, but I can show you the basic idea. And in fact, let me just see if I can get this guy over here. So yeah, so this little illustration over here shows you that if you want the speed of light to be constant, and if you learn that time is not constant, then space can't be constant either, because what is speed? Speed is nothing but how far you go divided by how long it takes you to get there. And if the speed of light is fixed at 671 million miles per hour, and if time is something that is malleable, as we just saw, time in motion slows down, then space has to also have a reaction to motion, because it has to react in just the right way to cancel out the slowing of time, to keep the speed of light, namely the ratio of space per time, to keep that fixed. So that's the basic idea, where you learn immediately that space has to also be affected. But let me show you now what that effect looks like. So here's a taxi cab traveling along. I'm gonna go, where should I sit for these guys? Yeah, I guess this is a good location as any to sit. So let me show you this again. This is a taxi cab that is speeding down the street in Manhattan. And look at that taxi cab. It's squeezed along the direction of motion. This is what you'd actually see if you could see things that are moving near the speed of light, and if a New York City taxi cab could travel near the speed of light, this is what you'd actually see. Space is crushed, squeezed, Lorentz contracted along the direction of motion. So those are the big effects of the special theory of relativity, and they're deep, right? I mean, they're absolutely deep, and the reverse, I should also say, is true. We, in this little animation, are on the sidewalk looking at the taxi cab as it is streaming by, right? But you could also ask yourself, what if you're in the taxi cab looking at the outer world from the perspective of an object that's moving near the speed of light? I think I can show you that one too. I think this will show it. Yeah. So here we are inside a taxi cab. Here I am driving along near the speed of light, facing the wrong direction. Normally you face forward, right? I have to sort of face like this. But look outside. So the world, it's shrunken. It's actually even curved in along the direction of motion. That's because when we see things, we see them because the light has to travel from the object to our eyeball. And if the light is traveling from different locations, it will travel different distances, and therefore it will reach our eyeball at different moments. And therefore we're seeing a given object at different moments in time, because the light had to leave earlier from a more distant location to reach our eye at the same moment that the light is traveling from a nearer location. So that's cool. That's what a city block would look like if you're streaming along near the speed of light. So, it's kind of cool stuff, and it's unintuitive stuff. And that's how the world works according to Albert Einstein's special theory of relativity. So let me take a couple of questions on it. I see one here from Aryan Tiwari. If we move the light clock, why doesn't the speed of light relative to us be greater than the speed of light? Yeah, Ariane, you're asking the deep and important question at the heart of fundamental physics. You would think, Ariane and everybody else, that if you, for instance, turn on a flashlight while you're running forward, you would think that your forward motion would kick up the speed of light to be a little bit larger than what it is when you turn on the flashlight from a stationary position. I mean, that's why in the game of cricket, why does, what's it called? The dude who throws the ball in a game of cricket, the bowler? I don't know, you guys, I know some of you are from India, so please correct my terminology. But in baseball, the pitcher doesn't run forward, but in cricket, the bowler does run forward. Why does the bowler run forward? Because the bowler knows that the bowler's motion forward will be transmitted to the ball that the bowler is throwing forward, and it will go faster, right? You can make the ball go faster by not throwing it from a stationary position. Rather, you throw it or you bowl it, if that's the correct language, from a running forward position. It's so intuitive. It's so basic. It's how the world works in an everyday sensorial experience. But that doesn't translate to light. If you run forward while turning on a flashlight, the speed of the light is exactly the same as it would be if you turn on the flashlight as at rest. Your forward motion, unlike the case of cricket, does not add any additional speed to that which is intrinsic to the light itself. Now, Ariane asks, why is that? Answer, I don't know. I do not know why the speed of light is constant. Nobody really knows why the speed of light is constant. Let me take the word really out. Nobody knows why the speed of light is constant. We do know that experiments and observation establish that the speed of light is constant. And we do know that if you're Albert Einstein, you can use that fact to deduce other qualities of the world that are completely unexpected, like the slowing of time for a clock in motion, like the squeezing of space for an object in motion. But Ariane, could there be another reality, another universe in which the speed of light is not constant? Sure. I don't think there's any logical necessity of the speed of light being constant, and yet it is. And all we meager human beings do is extract the consequences of this fact of the speed of light being constant. And among those facts, among those consequences, I should say, are the ones that I've shown you: the slowing of time and the squeezing of space. So that's, as far as we know, that's how it all works. And it could have been different, but apparently it is not. So Coco asks, if the time slows down for a moving clock, shouldn't the rate at which the said clock goes decrease instead of increase as shown by the Lorentz transformation? It's really irritating for me. I'm trying to understand the question, Coco. Let me just read it again. If time slows down for a moving clock, good. Shouldn't the rate at which that clock goes, I guess moves, decrease? And so, oh, I see what you're saying. Yeah, good. I understand completely. So here's the thing, Coco. Imagine that instead of a clock in motion, you're watching me in motion, and I am, say, walking across. And you say, time for me is slowing down. Now, what does that mean? What that means is if you look at me carefully, you will see me slow down. You will see me in slow motion. You will see my head turn slowly. My eyes will blink slowly. Everything about me will be in slow motion. So that's the sense, Coco, in which the said clock will decrease. That's the sense in which the object in motion will experience time slowing down. My own speed, let's say I'm on a skateboard or I'm in a car, my speed won't slow down, My speed is one of the givens of the physical situation. Our relative motion is what we are given. And we are saying that you looking at me, you are seeing my bodily form in aggregate moving at a certain speed near the speed of light. That's a given. But when you then look at my intrinsic motion within that vehicle that may be traveling near the speed of light, you will indeed see me going slower. You will indeed see time slowing down for me. And in fact, if I look back at you from my position in the car, I will see you in slow motion. Your eyes will be blinking slowly. Your arms will be moving slowly. So that's the sense in which the moving object appears to be in slow motion. Its own intrinsic speed from being in the vehicle is part of the given information of the physical situation that we're analyzing. I hope that, Coco, if that doesn't do it for you, ask again. But that's the key idea. Orcus ifstitia. Sorry, again, you know me. I'm awful on learning how to pronounce names, but ORCVS, ifstitia asks, have you figured out why any of the constants are what they are? And of course, among those constants is the constant speed of light. Why do the constants have the values that they do? Well, from one perspective, when it comes to the speed of light, there's nothing special about the number 300 million meters per second, 186,000 miles per second, 671 million miles per hour. You see, I'm doing this because you see that the numbers change depending on your units. So it's merely, you choose a unit for measuring distance, you choose a unit for measuring time, the second or the hour for distance. It could be the meter or the kilometer or the mile or the inch, whatever. You choose your units, and then the speed of light is some particular number in those units. But that number is not special. It totally depends on the units that you choose. In fact, if you choose your unit to be for distance, to be the foot, I know it's the archaic English system, but whatever. And if you choose the duration of time to be measured in nanoseconds, then the speed of light is very close to 1 foot per nanosecond. 1 foot per nanosecond. So it's 1. Speed of light is 1 in those units. So there you see, you can make it any number that you want. The deep question, though, is if you look at ratios of these constants of nature, ratios that have no units. For instance, the mass of the electron divided by the mass of the up quark. That's a number. That's unit independent. Whatever units you use for the mass of the electron and whatever units, if you use the same one for the mass of the up quark, if you take the ratio of those two masses, then the units drop out and you're left with a pure number. And that pure number cries out for explanation. And that, Orcus, is really the question that you're asking. And no, we've not made any progress on understanding those dimensionless, those unitless ratios. We don't know why the electron mass to the various quark masses have the values that they do. We don't know why, the fine structure constant, which, as you know, is a ratio of electric charge and Planck's constant, the speed of light. We don't know why it has the value 1/137 at particular energy scales. We don't know why. And that's one of the deep questions that we hope one day to answer. But as of today, we don't. Look, one answer, I should say, a far out answer, is that maybe we live in a multiverse, right? Maybe we live in a multiverse. How does that help? Well, remember what the multiverse is, right? I can even show you a little kind of picture of the multiverse, I think, right? So there's the multiverse. So each of those spheres represents a different universe. And our universe would be one sphere in this grand collection of different spheres, different universes. Now, why is that relevant to the question that was asked? Well, imagine that in each of those universes, the constants of nature may still be constant, but they might have different values. And that would mean that the values and the dimensionless ratios, that's an environmental feature of the world. It's not a fundamental feature of the world. It depends on which of these bubbles you're in, which of the spheres, which of the universes in the multiverse you happen to inhabit. And that's one possible answer. And that answer would be there's no fundamental explanation of the fundamental constants of nature. They vary from universe to universe. And perhaps the values that they have in our universe are special because they allow for the chemical and biological and physical processes necessary for our form of life. So maybe the answer is not some fundamental physics explanation, but rather the constants of nature have the values they do because when they have different values, as they may in other universes, highly speculative idea, those universes aren't planets and people. So the answer might be one of environmental influence as opposed to some sort of fundamental first principle explanation for why the constants have the values that they do. I'm being told I'm out of focus and my webcam needs to refocus on me. I don't know how to do that, guys, but you know, I can sort of try to do that. You know, I'm not a particularly good person when it comes to these kinds of things, but I'm gonna shut off the autofocus. I'm gonna turn on the focus. I don't know, that looks pretty good. So let me know if that helps, guys, because it's kind of irritating to view things that are blurry for the next period of time that we have together. Hopefully that helped. But let me know in the chat or wherever you can. I'd appreciate that. Okay, so carrying on with your questions. Kirag, oh, come on, that was a good question, Kirag. And now I touched my scroll and it ran away from me. I'm so sad. That was a good multiverse question. Perfect question to go into. Okay, I'm told at least that I fixed the focus problem. So let me know if that happens again. So Kirag, ask your question again. It's somewhere in the feed and I lost it. I think it was a multiverse question. Akash Shalar asks, is the universe expanding at different rates at different locations? And it depends what you mean by universe there. If by universe you mean, you know, the multiverse, which again, I'm not saying that there is a multiverse, but it's an interesting idea worthy of consideration. Then of course, in the different universes, space could expand at different rates. In our universe, as far as you know, the observations seem to strongly suggest that our universe is isotropic. Isotropic means that regardless of the direction that you're looking, the physical features and the physical properties on average are the same. And that suggests that the rate of expansion in the different three dimensions that we know about, those rates are the same. And they're also the same in the sense of homogeneity, namely, regardless of where you are, the expansion rate is the same. So homogeneity and isotropy lead to the conclusion that the expansion of space is the same regardless of where you are located and what direction you are measuring. But, you know, in a theory like string theory, which has extra dimensions, I wish I had some extra dimensions stuff that I could show you, but I don't have anything in my little goodie bag over here at the moment. But by the way, you should tell me if you enjoyed these visuals. You know, I thought it'd be kind of fun to spice things up for this launch of World Science U, which is a highly, highly visual platform for discussing all these ideas, not just relativity, but, you know, cosmology and consciousness and neuroscience, symmetry. Again, you should really check out World Science U because it's a great opportunity to learn from the great thinkers of the world. But it's such a visual platform that I thought it'd be fun to introduce some visuals. Normally I just show you my real background right here that you see, you know, behind me right now. It's sort of a nice day out there today, but I don't have any extra dimension stuff to show you. Maybe next time, but you should tell me, do you find the visuals fun in this context or do you find them irritating? So kind of just let me know on that in the chat. I'd be interested to know. But the reason I bring up extra dimensions relevant to this question of the expansion of space, it's certainly possible that in the very early universe, all the dimensions, assuming string theory is right, So the 3 dimensions of space that we know about, together with the extra dimensions of space that string theory requires, imagine that they were all very tiny early on. And imagine, much in line with the question that was asked, the rate of expansion of those dimensions was different. Imagine that the 3 big dimensions that we know about, left, right, back, forth, up, down, that these 3 big dimensions expanded far more quickly than the rate of expansion of the other dimensions of space. And that's why we are all familiar with the 3 big dimensions of common experience, because they grew large enough that we have direct access to them through our vision, through our eyes. And imagine that the other dimensions are just as real, but they either didn't expand at all, or they expanded so slowly that they're still so tiny that we don't have direct access to them through everyday experience, through our eyes. So that would be a nice application of the question to give an explanation for how it's possible in a theory that posits more than 3 dimensions of common experience, how it's possible that we would only be aware of 3 of those dimensions, a subset of those dimensions. One possible answer is what the questioner asked. The answer might be that the 3 dimensions you know about expanded much more quickly than the others, and that's why they're much easier to see. All right, what else do we have in our question scroll here? Sanjal Prasad asks from the World Science Festival webpage, do you think that time travel to the past is possible? And I don't know about time travel to the past. I would say that the best answer as of today is that time travel to the past has not been ruled out. It's a real possibility in the sense that the door has not been firmly shut. And that means that creative individuals may find a way of walking through that tiny crack in understanding and one day establishing that time travel to the past is possible. If you ask me, though, to go a little bit beyond what we absolutely know and to speculate, my guess is that time travel to the past is not possible. My guess is that time travel to the past will one day be ruled out, fully, firmly done. But time travel to the future, which you didn't ask about because I suspect you know the answer, time travel to the future is possible. It's exactly what I was saying early on when we talk about time slowing down for a clock that's in motion, right? You put that clock on a rocket ship, it goes out, it comes back. Less time will have elapsed on that round trip journey than on your clock on planet Earth. So when that space traveler steps out of the portal in that rocket ship, they will have aged less than you. They will have aged less than all of Earth has aged. What does that mean? That means they have jumped into the future. To jump into the future is simply to find yourself in a circumstance where the environment around you has aged much more than you have. Literally, in the sense that the amount of time that's gone by. 1 year for you, but 1,000,000 years for everybody else means that you have jumped into the future by roughly 1,000,000 years, or 999,999 years. That's what it means. And that is within the understanding of physics as we know it. Another interesting question along these lines, Giannis asks on the World Science Festival page, so if you go to the past, you go to your own past or in a parallel universe past. And that's a very important question to ask. Again, number one, I don't know if it's possible to go to the past. Number two, I don't even know if there are other universes. So speculation 1 and speculation 2, but be that as it may, let's carry on and imagine what the possibilities might be. And people have speculated that if you could travel to the past, you would go to the past in a parallel universe, not in your own, simply because that's a way of getting around this famous grandfather or grandmother paradox. Remember what that paradox is. If you can go to the past and perhaps prevent your grandparents from ever meeting, then you would never be born, right? Because your parents would never be born, so if that's the case, how were you ever there to effectuate the change that kept your parents or grandparents from meeting in the first place? That's the paradox. How do you solve that paradox? Well, as Giannis asks, if when you travel to the past, if you can, you find yourself always in a parallel universe, not the universe from which you originated, then the question of your birth no longer poses a paradox. You were born in universe number 1. You travel to the past in universe 2. In universe 2, your grandparents never met, your parents never met, you were never born in universe 2. But that's not paradoxical any longer because you were born in universe 1. Your origin is no longer cause for consternation if when you travel to the past, you travel always to a parallel universe. So that's why people talk about this idea. And yeah, you know, it's not ruled out. People have used ideas of special and general relativity to even suggest ways that you might travel to the past. But as yet, I'd say it's highly, highly, highly speculative. And again, my gut feeling is that one day it will be ruled out. Okay, so let me just carry on with some of the questions in the live chat. Claudio Barrosa asks, how do you know if a body is stationary, not moving in the universe? And the answer is, let me give 2 answers to that. Number 1, fundamentally speaking, there is no answer in the sense of there's no absolute notion of rest. So the only time that you can really ever talk about speed is when you're talking about the speed of one object relative to another. So you can't say that an object is moving in the universe, period, end of story. You can say object number 1 is moving relative to object number 2. And you can say object number 2 is moving relative to object number 3. But if these objects in principle are moving at a fixed speed and a fixed direction, and they always have been and they always will be, then each of those objects can claim to be at rest, can claim to be stationary, and claim that the motion that's taking place is motion relative to their perspective, to their frame of reference. And that's something that every object moving at a fixed speed and fixed direction can validly claim. Now, why do I say fixed speed and fixed direction? Because if it's not fixed speed and fixed direction, if there's acceleration or deceleration, which can be speeding up or slowing down or going around a bend, not in a fixed direction, then that object can feel intrinsically that motion. And that object, therefore, can claim to be in motion and cannot claim to be at rest. To claim to be at rest, you have got to satisfy certain conditions, which roughly speaking can be summarized by saying that you don't feel any motion. Otherwise, you are absolutely in motion, but there's no notion of absolute rest. Now, I said I was going to give 2 answers. The second answer is, well, practically speaking, what do we mean, for instance, about the age of the universe when we say that it has a particular age, 13.8 billion years, right? On whose clock? And the answer to that is it's on those clocks for whom the observer moving with that clock would see the cosmic microwave background to be homogeneous and isotropic, that it won't have a preferred orientation moving with respect to the cosmic microwave background radiation. So in a certain sense, cosmologically speaking, there is a preferred frame of reference. It's that one for which the background radiation has that particular property. But putting cosmology to the side, just thinking about an object moving through space, no preferred frame of reference, no absolute notion of being at rest. Okay, let me go back to the feed here. Charles Maurer asks, if time stopped and reversed direction, how would we ever know? Wouldn't we unremember all those moments? Couldn't time always be moving back and forth? And the basic point that you make, Charles, is an absolutely valid one. The individual, if the change in time, speeding up or slowing down, is a true property of the physical universe. And if that individual's thoughts are nothing but a product of the physical processes within that physical universe, then the individual never experiences time doing anything odd, right? I mean, you're going back and forth and remembering and unremembering. That's a little bit more complex and it's a little bit more subtle, but you can ask the same question using the special theory of relativity example that I was giving you before. I mean, look, if someone is carrying this clock in motion, right? So the clock is in motion and time is slowing down from our stationary perspective on that moving clock. You can see it, it's ticking off time more slowly. What about the individual that's moving with that moving clock? Well, they experience time slowing down. And the answer to that question is they won't experience time slowing down at all. Because when we talk about the light clock showing less elapsed time, we're talking about time, real time. And because we're talking about real time, it applies not just to the light clock that's slowing, but it applies to biological processes, chemical processes, physical processes, neurological processes. So the individual carrying that light clock in motion, the neurological processes responsible for their experience will slow down. Their thoughts will slow down. And therefore, as they look, for instance, at their clock, they look at their environment, it will appear to them that nothing has happened. If they look back and by comparison look at our stationary clock, they will say that our stationary clock has slowed down. But their intrinsic experience, the number of books that they could read in their lifetime, will be the same, regardless of whether they were with us sitting still or with that moving clock. Their life will elapse in slow motion and they won't feel it, they won't know it because their thoughts are slowing down too, because their thoughts are a physical process. So in that sense, the individual, without reference to other external points of comparison, the individual does not experience, say, the slowing or the speeding up of time. So Coco has come back with a follow-on question. I like follow-on questions. And Coco says, but sir, why does a second manifest a bit more than a second on a moving clock? Wouldn't that imply that more time has passed for the moving being than in 1 second of the non-moving one? Yeah, this is always a point of confusion. And when we say that time has slowed down on the moving clock, here's what we really mean. What we really mean is for that moving clock to go tick tock, okay, and thereby register 1 on the counter on that moving clock, tick tock. We look at our stationary clock and say our stationary clock goes tick tock and a little bit more. So more than 1 second goes by on our stationary clock when 1 second has gone by on the moving clock. That's the sense in which time is slowing down on the moving clock. It takes more than 1 second for its clock to go tick tock. Why? Because it's ticking off time more slowly. That's the colloquial language. We say it's ticking off time more slowly because it's going tick tock. Well, our clock is going tick tock, tick tock, tick tock. That's the sense in which less time elapses on the moving clock. I hope that addresses the question, Coco, but come back at me if I missed your point or if you're not convinced by that explanation. All right, I'm scrolling through some of the live chat questions. And Chris Arun asks, what has that to do with age? And I say, Chris, that it has everything to do with age. Age is nothing but a reflection of the physical processes that are taking place in your body. And if those physical processes are taking place at a slower rate, then you are aging more slowly. So if I'm looking at you carrying that moving light clock, just that we can have a very specific image in mind, I look at the light clock in motion and it's going tick tock because the light's going on that double diagonal, that longer trajectory at the same speed. So I'm watching your moving light clock is going tick tock. I conclude, therefore, that time is slowing down for you in motion, and that time refers to true time. It's time. It's not some weird thing that a light clock measures. It's what we mean by duration. And therefore, if time is slowing down, then the molecular processes in your body are slowing down. The neurological processes in your brain are slowing down. The rate at which you are aging is slowing down. And that's why this has everything to do with age. I mean, sometimes people, they understand the light clock, but they leave the example thinking that it's just some weird property of some weird contraption that happens to have two mirrors mounted in a parallel manner facing each other with a ball of light bouncing in between. But it's not just some weird feature of some arbitrary gadget. What we're actually tapping into is the rate at which time itself is elapsing. And the light clock is merely a simple tool to measure the rate at which time is elapsing. We could do it with any watch, grandfather clock, Rolex watch, the clock on your iPhone. It doesn't matter. The only reason I use the light clock is because the inner mechanism is so fantastically simple that with a little animation and a little thought, we can conclude that the tick-tock on the moving light clock is going slower. It's the simplification of the inner mechanism that allows us to do that. But although the journey would be more complicated, we can do the same thing for any clock, regardless of the mechanism. It's just harder to come to the conclusion. And I'm in favor of easier ways of getting to deep conclusions than hard ways to get at deep conclusions. And that's why we use the light clock. But don't be fooled into thinking that the conclusion is somehow only relevant to the light clock. The conclusion is relevant to time itself. You want an argument for that? I'll give you an argument for that. Take your iPhone. Give it to me. Yeah, give it to me now. Okay, I'm going to take your iPhone and I'm going to strap it to the top of that light clock. And I'm going to set that light clock in motion, or assume that it's always been in motion so I don't have to deal with acceleration, but don't worry about those details. If you are now walking along with your iPhone and the light clock, from your perspective, you can claim that you are at rest and everything else is moving relative to you, right? Fixed speed and fixed direction, you can claim to be at rest. And because you can claim to be at rest, you, of course, are going to say that the tick-tock of the light clock and the tick-tock on your iPhone are in sync. We've set it up so they're in sync. And because you can now draw that conclusion, we who are watching you in motion say, aha, the phone, the iPhone clock, and the light clock, they are in sync. And therefore, if the light clock slows down, the iPhone must be slowing down too, because they are in sync. You've already established that by virtue of your ability to claim that you, the light clock, and the iPhone are all at rest and everybody else is moving relative to you. And how could any external motion affect the synchronization of your iPhone and the light clock? And therefore, the slowing of time on the light clock is the slowing of time on the iPhone, is the slowing of time on each and every clock. So again, I mean, clocks, they come in, you know, all sorts of shapes, all sorts of styles, you know, You know, here's a kind of fun little animation showing the kinds of clocks that we have invented over the course of our species, right? From sundials to old-fashioned alarm clocks, you know, to quartz crystals, to whatever. My claim is the conclusion that we reached regarding the slowing of time in the light clock, it applies to each and every one of the clocks that you are seeing and each and every one of the clocks that you can imagine. As long as that clock is indeed ticking off in a regular manner, as long as that clock is somehow advancing forward in a regular manner, equal intervals between the numbers or the ticks or the blips, whatever mechanism it uses, all of that will be happening slower if that clock is in motion relative to us. If we're looking at that clock in motion, we will conclude the time is elapsing slower on that clock than on ours. It is a completely general conclusion about the nature of time. So Chris, that's Chris Arun. Maybe that was a more involved answer than you anticipated, but I hope that convinces you that what we're talking about with the special theory of relativity has everything to do with age, because it has everything to do with time. Alrighty, so I'm going to continue our session, your daily equations session, but I wanted to kind of draw a little bit of a break between the World Science U live session, focusing upon the special theory of relativity. Again, I really do encourage you guys to check out my course there at World Science U, which explains all these ideas. And somebody asked if there's the math behind it, and there is. So there's two versions of the course. The one at the moment that's up there is the non-mathematical version that explains the ideas in the kinds of language that we're using here today. But those of you who like math, and I know some of you do, the math version of that will be reposted. It's been up before, but it's going to be reposted in a newly revamped and refined architecture for the experience. So I think you'll enjoy that. And there's 5 courses there right now, and we're going to be releasing new classes about, I think, on the order of 1 per week for the next 30 or 40 weeks. And the faculty is, second to none, some of the great thinkers in the world. So you should go check it out, World Science U. But I'm not going to segue a little bit to focus on, if you want to ask relativity questions, more than happy to. But I would now like to address any and all questions that you might have in mind. So just throw them at me, and I'm happy to field as many as I can. All right, so what do we have here? The U-Bose asked, Dr. Bose requests to comment on if a potential imaging technique can be devised to select cancers over non-cancer cells. And I would say, Dr. Bose, thanks for your question. It's not my field of expertise, so I can't really help you there. I mean, you all know that the way MRIs work is by using the ability to modify the spins of particles in a magnetic field and to thereby access the qualities of human tissue based upon the kinds of blood flow that they support. And doctors and researchers have gotten very good at distinguishing different kinds of tissues by virtue of the different kinds of signals that they yield inside a magnetic resonant imaging device. But beyond that, unfortunately, Dr. Bose, you're at a level of medical detail that is beyond my knowledge. So I'll encourage you to ask that question to somebody who's in the medical field. Suman Acharya asks, is time an emergent property? What is your thought? And, it's a hard question. And I don't know. Nobody does. I guess my suspicion is that time is an emergent property. My suspicion is that time is a very useful way to organize experience. And that's why it naturally emerged in the course of our species. And that's why we all have a deep intuition about time, right? Now, that intuition is not accurate when you're considering physical situations that are remote from human experience, right? So near the speed of light, who would have thought that time slows down? And yet, as we've been discussing, it does. Who would have thought that time slows down near the edge of a black hole? We don't experience these things, and therefore they lie outside the purview of our intuition. So my guess is that the qualities of time that we hold dear and the ubiquity of time as an organizing principle. I mean, we can't even go half a sentence without talking about the past or the future or the present in some way, shape, or form. We conjugate verbs based upon the tense. So we can't get out of a temporal way of thinking about the world. And I suspect that's because that way of thinking about the world had evolutionary advantages. And we therefore evolved in a way to think about the world in temporal terms. But are there other ways to think about the world? And is it possible to imagine a non-temporal way of thinking about the world? Is it possible that time is emergent in this sense? I think it's quite possible, yes. All right, let's see. Francis Serafini says, to Coco, if you see him as blinking slower, he then has to see you as blinking faster. And that's an interesting comment that is not completely true, actually. So you would have thought that in special relativity, let's be concrete, that if you see me blinking slower because I'm in motion and you're watching me and time for me, from your perspective, is slowing down, you would think, therefore, that the symmetry of the situation might suggest that you see me slower, I see you faster, and that's not right. So if I am moving away from you, I can equally claim that you're moving away from me. And then the symmetry of the situation is even more deep than you would have thought based upon a cursory analysis of the situation. Everything that you did to conclude that I am in slow motion, whether it's through observation or mathematical calculation, I can do regarding you. And so you will see me blink slowly and I will see you blink slowly, not faster. And that is a curious quality of the situation. Now, there's something else that I should bring up, which is a little bit confusing, but keep your head on straight. If I am not moving away from you, but rather I am moving toward you, then the intrinsic effect of time slowing down, because I'm a body in motion and you're watching me, that is overwhelmed, as it turns out, by a separate but related effect, the Doppler effect, where the light that's traveling from me to your eyeballs has to travel an ever less distance, has to travel an ever shorter distance from my face, say, to your eyes as I'm approaching you. And that shortened distance that the light travels makes it appear that I'm speeding up, right? Because as I'm blinking, the light from when my eye is open and the light from when my eye closes, the light from my eye closes doesn't have to travel as far. Therefore, it in some sense gets to you more quickly than it otherwise would if I were stationary. So as I'm traveling toward you, you will see my eyes blink more quickly, and I will see your eyes blink more quickly. Now, you might think that that would suggest that time is speeding up, but it's not. If we carefully unravel our observations of the eye blinking more quickly, we will realize the time intrinsically is slowing down, but this Doppler effect of the light having to travel a shorter distance makes it appear as though my eyes are blinking more quickly. So, and it's again completely symmetric. I see you blinking more quickly, you see me blinking more quickly. In the reverse, not the reverse, but if I'm moving away, You'll see my eyes blink more slowly. I will see your eyes blink more slowly. Perfect symmetry. You might say, well, okay, then how does this answer the twin paradox? It does in a very beautiful and simple way. Maybe I'll leave it to one of you to give that answer. In fact, maybe I'll bring in some visuals next time to show that. Bottom line is, just for you who are interested, and this actually is covered in one of the modules in the special relativity course. To the person in motion, half of the journey, if they had a powerful telescope, look back on planet Earth, half of the journey they'll see my eyes blinking slowly, and half, namely on the return, they'll see my eyes blinking more quickly. For the person on Earth, namely me, looking at the space travel, let's say it's you, I will see your eyes blinking slowly for a much longer fraction of the journey than one half. Why? When you turn around and come back, I don't see that you've turned around yet, because the light from your turnaround has to travel all the way back to my eyeballs for me to see it. So it takes a long time for me to recognize that you've turned around, which means it takes a long time for me to see your eyes blinking quickly. So for the majority of your round trip journey, I see your eyes blinking slowly. And just for a little bit at the end, I see your eyes blinking more quickly, which means overall, I will have seen you more in slow motion than in fast motion. You will have aged as I watch you less than you will have seen me age, where half of my time, half of the journey, I'm slow and half I'm quick. There's where the asymmetry comes in. The person who's actually in motion has to turn around and come back. And when they turn around, they immediately know that they've turned around. They felt the motion, and they immediately are encountering light signals that are subject to this blue shift, the subject to this Lorentz, this Doppler effect. That's the difference. That's where the asymmetry comes into the story. If that's confusing to you, don't be upset. It's a complex idea. I spell it out visually on World Science U. So again, not to plug it too much, but worth checking that out. Okay. Ellen asks, is math brain a myth? Can an adult still learn? And it's half a myth and half not a myth, Ellen, I would say. So it's not that the adult brain can't somehow learn things that the younger brain can. It's just harder, I found, for the adult brain to do so. And certain tasks, neuroscientists have studied the plasticity of the brain, and the brain is more able to take in novel behaviors and novel concepts when it's in its most formative stages. And therefore, we see it. You want to learn piano, do it as a kid. I tell this to my kids all the time, and they roll their eyes, which hurts me to my core, because you all know, you've met so many people, maybe you yourself have fretted over the fact that you gave up piano. You say, why did I do that? Because now when you try to go back, it's so much more difficult. So much more difficult, because your brain doesn't have the plasticity that it once did. And therefore, it's harder for it to learn new tricks. So there's something to be said about that for mathematics. I mean, math prodigies have the ability to absorb math at an astounding rate. And I don't know a single example of a math prodigy whose prodigious talents emerged in adulthood. I mean, maybe there are examples. I'd be interested to hear about it. But I don't know of an example, and it kind of makes sense to me, because the brain is more set in its structural form after whatever, I don't know what the age is called, 20 or 20 plus years. And it makes it harder for that brain to do the kinds of things that a younger brain does with ease. So Ellen, yes, you can learn math at an older age. It's just more difficult. One, Emelka asks, if two objects in space move away from each other and we don't know which one is actually moving, who is time going to slow for? And I love the question, one, Emelka, because it highlights, I don't mean this in a mean sense, but it highlights a real confusion that many people have, not just you. Look at the language that you're using, one, Emelka. You say if two objects in space are moving away from each other and we don't know which one is actually moving, you have in mind that there's a notion of absolute motion and absolute rest. And there isn't. There is no notion of which is actually moving. Again, I'm assuming fixed speed, fixed direction. You know, they're moving, say, away from each other like this. There is no absolute answer to the question of who is actually moving. They're moving relative to each other. And what that means is, if one of those objects looks at the other, this observer will say that that observer's clock is ticking off time slowly. If that observer looks back at the first object, that observer will say that the other observer has a clock that's ticking off time more slowly. And that's it. There's no absolute notion of time. There is no absolute notion of time slowing down. That has in mind there's some grand cosmic clock in the Newtonian sense. That's the real clock that really measures time, and we are comparing to it, but there is no such cosmic universal time. There is no such cosmic clock. It is time from one person's perspective relative to time from another's perspective. And that's it. There's no notion of absolute rest. There's no notion of absolute constant velocity. There's no notion of absolute time. It's always one relative to another. Okay. Let me see what else we have here. Zero Oskil asks, why do you use Newtonian gravity and Einsteinian gravitation as interchangeable terms? Oh, I hope I don't. I hope I don't. When I'm talking about Newtonian gravity, I'm talking about the kind of gravity described by F equals G m1 m2 over r squared. It's gravity that exerts an influence instantaneously across any distance. And it's the version of gravity that was put down in the late 1600s. When I talk about Einsteinian gravity, I'm talking about gravity that follows a different equation, r mu nu minus a half g mu nu r equals 8 pi g over c to the fourth t mu nu, Einstein's field equations. And it's a version of gravity that differs from the Newtonian one in situations that involve large speeds, large velocities, and exceedingly large gravitational fields like those of a black hole. So if I've given you the impression that I'm conflating Newtonian gravity and Einsteinian gravity, I apologize for that. I'd like to know further where you thought I was conflating them, because at least in my mind, maybe not in my language, I keep them quite separate, quite distinct. Okay. G-Cell asks, is it possible that the speed of light in the far future is faster? And yes, there are people who have discussed what are known as VSLs, variable speed of light theories. And they've exacted a degree of controversy from the community. But the notion that the speed of light at one moment and the speed of light at another moment might be different values seems to me a logically possible way that the world could behave. Speed of light, you measure it on whatever, July 23rd, 2020. You measure the speed of light on July 24, 2020, and you take the ratio of those numbers. And it seems logically possible that that ratio would not be equal to 1. And some have wondered if the speed of light was very different in the early universe, whether it might help address certain cosmological puzzles that we have fretted over. I don't think these theories have really gathered a great deal of support in the physics community, largely because there's no evidence for the speed of light changing over time. But as a logical possibility, yeah, I think it is an absolute logical possibility. ALAA asks, Professor, are dimensionless physical constants rational or irrational? And I see no reason why these ratios can't be irrational. when we measure a physical quantity using a real device, we measure it to a certain degree of accuracy, and therefore we measure it as a real number to a finite number of decimal places, which means, of course, we measure a rational number. And therefore, when we take the ratio of two measured constants of nature, it's a rational over a rational. So it would be, I hope I said that clearly, it's a rational divided by another rational. And therefore, that quotient is also a rational number, not an rational number. But those are just measurements. I don't see any fundamental reason why the constants of nature might not be like pi or E, and therefore irrational. So in answer to your question, I don't see any reason why they can't be irrational, but maybe if you have an argument otherwise, I certainly would be game to hear it. All right. Charles Maurer, if we looked at a black hole, shouldn't we see everything that has ever fallen into it around the event horizon? Aren't we seeing those objects time approach zero? And the answer to that is yes. So from the perspective of somebody outside of a black hole, watching an object heading toward a black hole, you're absolutely right that much as in the light clock in motion, although the argument is more involved, but similar to that, you would find that time on a clock of an object heading toward the event horizon of a black hole would tick off ever more slowly. And as that object got right to the horizon, the rate at which his clock would tick would approach zero. You're absolutely right. So from our perspective watching it, it's as if the object not just goes in slow motion as it's approaching the event horizon, it actually freezes. Now, why don't we see that? Well, the light that the object gives off has oscillations that go ever more slowly, which means a wavelength that grows ever longer, which means that it's redshifted. In fact, as it approaches the edge of a black hole, the light that we receive from that object is infinitely redshifted, which means that it becomes increasingly difficult to actually see that object. So in some sense, all the objects that fall into a black hole from our perspective are there on the horizon, but they're so redshifted that we can't ever see them. Now, again, that's a very different story from the perspective of the object itself. From its perspective, it's just going along and it crosses the event horizon, it falls in and gets crushed at the singularity, according to the classical general theory of relativity. So again, it's two very different perspectives. They're mutually compatible, but the stories that we tell are quite different from one another. And that's the lesson of relativity. We have to admit distinct narratives describing reality. They can't be mutually contradictory narratives, but they can be different narratives. And here's an example where the narratives are quite different. They're not contradictory, as I've described it. People have tried to find contradictions, and interesting insights have emerged from those studies, and that's a whole different story. But there are different narratives describing reality based on the perspective that you take. Okay, carrying on. So Gokul, Monjeb's TV. When two particles are collided, some of their energy is lost. Where does it go? Could it go to another dimension? If yes, then is it possible that some energy may come from another dimension to our dimension? And in brief, the answer is yes to all those questions. In fact, one of the ways that we'd hope to gain experimental evidence for the existence of other dimensions is through proton-proton collisions at the Large Hadron Collider. The hope, Monjeb's TV, is exactly the question that you've articulated. The hope was that proton against proton slam together, very high speed, And some of the debris from the collision, according to the math of string theory, might be ejected out of our three-dimensional space and get crammed into another dimension of space. How would we notice that? Well, you measure the energy just before the collision. You measure the energy remaining after the collision. And if some of that energy has disappeared into another dimension, you'll have more energy before the collision than after it. Missing energy signature. Now, we've looked for those and we have yet to find any missing energy signatures. What does that mean? Number one, could be string theory is wrong. Could be that there aren't extra dimensions. Simple explanation. It could also be, however, that there are extra dimensions. It's just that they're so tightly curled up that the energy that you need to get into them, to seep into them, is larger than the energy of the Large Hadron Collider. And that's why we haven't seen any missing energy signatures. Or, it could be that, well, there are a host of other possibilities, but let me leave it at those two and thereby pivot to the second half of your question, which is, if in principle energy could go into the extra dimensions, if the Large Hadron Collider was bigger, if the extra dimensions were larger, could it be that energy could come the other direction? And in principle, yeah. In principle, yes. In principle, you could have energy seeping in, energy that we aren't cognizant of in our three big dimensions could show up. And that's a possibility. Now, don't go crazy on this idea. This doesn't mean all of a sudden that the ideas that you see in science fiction where somebody, snaps a finger and they disappear. You can say, oh, that's scientific, because what happens is their energy went into another dimension. No, it's not as though these possibilities can be realized in familiar physical situations. We're talking about extreme physical situations. But in those extreme situations, yes, energy can pop in from another dimension. Okay, let's see. So Chirag Baltha asks, are other universes also having the same speed of light, since the speed of light is constant? And I don't know the answer to that question. Number one, as I mentioned before, the speed of light in principle can vary in our universe. There are theories that have been written down, these variable speed of light theories that I've mentioned. And so, even in a situation that's not as exotic as, the one that you talk about. So, here's another way of thinking about the multiverse. So imagine that there's a big bang that yields, the grand expanse of everything. And within that grand expanse, imagine that little pockets open up where the energy transforms into particles. And each of those dark regions would be a universe. Now, that's a very exotic idea. And if the speed of light can vary in our universe, then you can certainly imagine it varying across the multiverse. But a related question that perhaps is more insightful is to ask, what about the dimensionless ratios, like the mass of this particle to that particle? Could that vary across the multiverse? And the answer to that is surely yes. And our theories allow for that kind of thing to happen. And as I mentioned before, that maybe gives us an explanation for why those dimensionless ratios have the values that they do. It's a different kind of answer. It's an environmental answer. It's not an answer where we say the mass of this particle to that particle had to be this value because of pure logic, or the only logically consistent theory of the universe demands that ratio have this particular value. That'd be a very convincing and satisfying explanation, but we don't have any evidence that our theories have the power to yield that kind of explanation. So the reverse explanation, championed by people like Lenny Susskind, is that those dimensionless ratios vary from universe to universe across the multiverse, and the value that those ratios have in our universe is simply the value, as I mentioned before, that allows for the physical properties and chemical processes and biological development that yields human beings and life as we know it. And the answer, therefore, for why the ratios have the values they do is much more situational. We are here and observe those values because those values are such that the physical and biological and chemical processes necessary for our form of life can take place. So that would be a distinct way of thinking about the explanation for the dimensionless constants of nature. Josh Antencio asks, when you die, will you promise to let us know if there is an afterlife? And Josh, you've got my word. If it's possible for me to let you know that there is, no, you know what, Josh, I'm going to take that back. I think there must be something powerful about not knowing the answer to that question. And I would not want to somehow eliminate the mystery of life after death from all human discourse. So I'm going to leave that as a mystery. You're going to have to get the promise from somebody else. Vishvesh Patel asks, what mechanism at the quantum level gives light its speed? What gives the photon the push from 0 to c instantaneously? The photon, when born, wouldn't have speed instinctively. And I would answer those questions in reverse. I would say the photon does have the speed c instinctively. I would say that there is no notion of a photon speeding up from 0 to c. Photons, as disturbances in the electromagnetic field, those disturbances always and forever travel at the speed of light. So there is no notion of an electromagnetic disturbance of the sort that isn't traveling at the speed of light. But then you say, you know, how to explain this at the quantum level? Look, we have quantum electrodynamics. Within quantum electrodynamics, we have a quanta, a minimum excitation, a minimum quantum excitation of the electromagnetic field that we call a photon. And within quantum electrodynamics, you see directly that the speed of this disturbance will be equal to the speed of light, and the speed of light being the number that emerges, say, from Maxwell's equations by considering the permeability and the permittivity of free space. And that ratio gives you the speed of light. And indeed, it's a ratio that comes right out of quantum electrodynamics. So I don't know if that's a satisfying answer, but that's one rigorous way that we can think about photons as disturbances, as quanta that have a very specific speed. Ayush Shrivastava, what happens to light after we switch off a bulb, as energy can't be created nor destroyed? And the answer to that is, when we turn off a light bulb, we are no longer exciting the electromagnetic field. And therefore, we are no longer emitting photons from the bulb. So as long as the bulb is on, as long as current is flowing through, we're able to excite the electromagnetic field, and the result is a torrent of photons that are emitted by that process. Turn off the bulb and you turn off the process, you turn off the emission of new photons. That's all there is to it. Neutrino says, no, there is no God. Sorry, you may be right, Neutrino. So we sometimes talk about those issues here. I'm not going to talk about it right now, but you may be right. Let's see if there's something on the WSU page. Oh yeah, a bunch of questions there. Sam Wilcox on the World Science U page asks, if past, present, and future all exist simultaneously, parenthetically, which I still have not understood exactly, does it mean we have no free will? Our future is fixed. And in answer to the free will question, yeah, you do not have free will. I would say that your future is fixed, though, in the sense that You're a collection of particles governed by quantum mechanical laws, and the quantum mechanical laws only describe the probability of one or other future for your collection of particles. So if that's what you mean by your future is fixed, namely the probabilities of this or that eventuality are fixed. Yeah, the probabilities are fixed, but the eventuality, what actually happens, is not fixed. So even though you don't have free will, even though you're fully governed by the mathematical laws that describe how your particles behave and interact, even though you don't have free will, I would say that your future, in the conventional intuitive sense of what will actually happen, is not fixed. So it's kind of an in-between place. You don't have any choice. You don't have any control. You don't have any willful ability to determine what will happen, even though what will happen is not determined as yet, because the physics only determines the probabilities of getting one or another outcome. Now, you'll notice that I didn't rely upon the first part of your question. The first part of your question was, if past, present, and future all exist simultaneously, then does it mean that I don't have free will? My argument that you don't have free will is more general than the one that you're anticipating. But the one that you're anticipating is compatible with this idea, because if the future exists, now that's a classical sense in which it exists. Special relativity is a classical theory. So in the sense of special relativity, that the future exists because my future might be your past, and therefore your past has already happened, and therefore in some sense my future has already happened because it coincides with your past if we are in relative motion. So yeah, I mean, the so-called block universe picture that this yields does have a future that is set in stone. So, but I would say in a classical world, if you're willing to go be classical, which is what this is, I would say you're done with free will from the get-go, because in a classical world, you give me the state of the world now, and I'll tell you the state of the world later. And therefore your will has nothing to do with the state of the world later. Your will is part of the unfolding. It's part of the sequence of events that gets us from here to there, or perhaps I should say from now to then. But it is not as though you freely exert your will, allowing you to contravene the mechanistic development from today till then. So in a classical world, it's done. There's simply no free will. In a quantum world, some people argue there's a little bit of room. I don't think there's any room at all, because if your will can't determine the outcome of the quantum events, then you don't have free will. But it is the case that there is greater flexibility regarding what happens, because the quantum laws only predict the probabilities. So, good and subtle question. All right, how are we doing here? 4:30. Boy, I don't have the stamina. I do have to build up to these long sessions. Some of you may know, by the way, and I'd be interested to know in the chat. You know, some of you know I did an hour before this live session on Reddit. You know, this RPAN, Reddit Public Access Network. You know, my book publisher. Some of you know I had a book come out in February, Until the End of Time. They've been encouraging me to do some of these Reddit sessions, you know, answer questions about the book and other things. So I did that from 2 o'clock Eastern time to 3 o'clock Eastern time. And then our session is on the heels of that session. So every other week I may do that. I'm not completely sure how long I'll do that. But so this is now 2.5 hours for me. So I'm going to try to go a grand total of 3 hours, which would take us to 5 o'clock, which would be a good hour less than the record that I've done in the past. But I'm feeling somewhat more exhausted, although I'm going to pump up the energy for the last half hour here. Easy Sparky, if you're tired, we understand. Thank you, Easy Sparky, but I'm going to give it my all for the last half hour. So don't think that I'm going to somehow shirk my responsibility here. But let me find some good questions that I haven't already addressed. Robinson Infant says, are you here in New York? It's 4:35 p.m. New York time. Yes, I'm here, humans. Yes, Robinson, I'm not in New York City, but I'm outside of New York City. You have kind of a, as you can see, it's kind of a nice space up here in the Catskill Mountains, a little gentle breeze behind me, which is kind of fun. But Dang Jose, I remember that name from when we were doing these sessions earlier, and I touched my scroll and I lost your question, Dang Jose. But I remember it from a half a second ago, reading it quickly. I believe Dang Jose was asking, how does relativity work if you take into account that the speed of light in, say, water is slower than the speed of light in a vacuum? And that's a well-known fact, that the speed of light in a vacuum is different than the speed of light in a medium, be that water or glass or anything else. And this has no impact on any of the conclusions, on any of the conclusions. Take a drink of water on that one. On any of the conclusions that we've been talking about. It's a well-known fact that as light meanders through a medium that's populated with atoms, the transmission of the light through that medium is slower than it is through a medium that isn't populated by a collection of atoms. So when I talk about the speed of light being constant, and I talk about the speed of light being whatever, 300 million meters per second, I'm talking about the speed of light through a vacuum. So bear in mind that that's what I mean when I make that statement. And the fact that the speed of light differs as speed traverses various media is well understood. And it fits perfectly within our relativistic description of things. So it doesn't in any way impact our conclusions. It just enriches the physical situations that we are able to describe. Cosmic Slice asks on one of our platforms, did you borrow Tracy's glasses again? And Cosmic Slice, you have a keen sense of the obvious. Indeed, I have. I do have another pair that I had around here someplace, but I couldn't find them. So in a last minute desire to be able to see what's going on, I have stolen Tracy, my wife's glasses again. So thank you for pointing that out, Cosmic Slice. Kirag Baltha says, sir, I love the chemistry between you and Dr. Neil deGrasse Tyson. Well, thank you. I've always enjoyed being on Neil's shows. He's a very energetic and very smart individual, and always has great questions and always makes it an enjoyable journey that we discover. I think the last thing I did was with him and Chuck Nice. I think I did, yeah, in Neil's office just before the lockdown and the virus hit. Maybe in the last thing that I did actually before the virus hit. And yeah, we had a nice little session, which was actually talking about my book. Oh, good. Gives me a nice segue back in. So we were talking about Until the End of Time, and we were taking audience questions on the book, and there were some great questions. So if you like Neil and you like the things that I talk about, go check out that segment on Star Talk Cosmic Queries. I think it was called Star Talk Cosmic Queries, if I'm not mistaken. Okay. Andre Zamfir, hi, Professor. Could you explain in a simple manner why M theory requires 11 dimensions? Andre, unfortunately, I cannot. I don't know how to do it. I don't often say that. Sometimes I say we don't know the answer. That's different. That's where research hasn't progressed to answer questions like what was before the Big Bang, or the ratios of the fundamental constants and so forth. Questions which I think we one day will answer. But when it comes to Andre's question, I don't have a simple intuitive explanation for why M theory or string theory in this more robust setting requires 11 space-time dimensions. I can describe it mathematically, and roughly speaking, the mathematics is very straightforward. You look at certain equations within the theory, and you imagine that the universe has any number of space-time dimensions, and you see that the equations only make sense if you have 11 space-time dimensions. So it's an internal mathematical consistency argument that drives you to this conclusion. But I agree that's not particularly satisfying. And when I wrote my first book, the elegant universe. I tried to answer that question, and I felt that I couldn't, and I was upfront about that in the elegant universe. And I've been upfront about it ever since. I can show you some nice visuals, and maybe I'll do it next time. I don't have any queued up, so it's hard for me to grab them quickly. But I'll show you some visuals of extra dimensions. In fact, I have a video out there right now. I don't know how I could show it to you. Probably can't. But I do have a video on hyperspace, on building 4-dimensional spaces and 5-dimensional spaces. You can find it on YouTube. I think it's on the World Science Festival YouTube page. I don't have the link. Maybe someone can send me that link in one of these pages, and I can then post it in the chat. That'd be kind of, never done that before. Yeah, in fact, sometimes people say that I'm not me, and I'll just tell you, I am me. Here I am writing in the chat. All right, so there you go. So I just I think there may be a time delay between what I say and what's in the chat, but there you go. So that truly is me. And if one of our folks would give us the link to this video, this YouTube video, which I show how to go from a point to a line to a square to a cube to a hypercube, you know, tesseract to a pentaract, and higher dimensional versions of those shapes. But I can't explain to you why it is that in an intuitive way, beyond using that mathematical explanation, for why it is that we need extra dimensions in string and M theory. Eddie Hernandez, can you come and give a lecture at Caltech sometime in 2021? Yeah, I'd love to. You know, Eddie, like everybody else, I don't know what the heck the world's going to be like in the near term, or even the time scale that you're talking about. You know, it's leaders who don't understand science, or who willfully ignore science, or who put politics above science, have gotten us into a tragic situation, especially in this country, right? I mean, other countries, some are having trouble too, but many other countries, they looked at the situation and they dealt with it. They listened to the scientists and the medical professionals and they dealt with it. But what did we do in this country? Some officials did that. Here we are in New York State. Cuomo did a good job. Listened to the medical professionals, listened to the science, and you see the curve, boom, nice and down. Other states, Georgia, Florida, Texas, didn't listen to the science, didn't listen to the medical professionals, opened too soon, and look at what's happening. And look, a country is a country. There are no borders in any real sense. We are literally in this together, in the sense that illness in one part of the country necessarily will infiltrate other parts of the country. So I don't know, Eddie. California too, right? Resurgent there too. But at least I think the reaction there would be more rational. So yes, if the world is better, I'd be happy to accept your invitation to come to Caltech in 2021, but I just don't know. All right, a few more questions before we wrap this up. M. Anderson, you're the best host. Thank you, M. Anderson. It gives me more energy to keep on going. But I'm not like the guy at the political top here. I don't need flattery, but I don't mind it, but I don't need it. That's the difference. Who doesn't like to hear nice things about themselves? But it is pathological when you absolutely need it and can't live without it and will do anything, lie, cheat, steal, break the law in order that you can get it. You know what I'm talking about, right? You know, it's sort of like Voldemort. I will not mention his name. And by the way, I did follow your advice. I've watched all Harry Potter films with my son, except film number 2. He wouldn't show me number 2 for some reason. He didn't like that. I've now seen all of the Harry Potter films. Loved it. It was great. So thank you for encouraging me to do that. But yeah, like Voldemort, I will not mention the name of the person to whom my small diatribe is referring. Okay, back to physics. Maria Mariu Cognac, I'm going into high school soon and I'm hoping to go into a field revolving around space. Do you have any advice for volunteering classes and so forth? And I would say, Maria, the number one priority is to do your work in school. study the basics hard, study the basics of physics and chemistry and biology and what other sciences your high school might offer. Learn the material inside out. Don't shirk that chore, which is vital, in favor of volunteering and doing research projects and things of that sort. But if you find that you can master all the material that you need to master and you still have additional time and energy on your hands, by all means, contact professors at a nearby university. Contact graduate students at a nearby university. Let them know that you're interested to work on a project with them. Look, I did this when I was quite young. When I was in junior high school, I had finished everything that my local public schools, IS 44 on 76th Street in Manhattan. I exhausted everything that they had to offer in mathematics. So a teacher gave me a letter, and I recently found this letter, right? I was telling you guys that my mom passed away. So I went back into her apartment and I've been cleaning out her things. And one of the letters I found was a letter that my 7th grade teacher wrote for me, gave to me, and said, go up to Columbia University and knock on doors. And the letter basically said, can you use this kid in some research project or some class or something, because he's hungry to learn? And I handed this to various people, and I handed it to one graduate student in mathematics, and he read it and he said, yeah, I'd be happy to teach you. We didn't have any money. It wasn't for any financial gain. And he met with me for multiple days over the course of weeks during the summer. Every Saturday, I would take the bus up to LaSalle Street, 125th Street in Manhattan, walk over to Claremont Avenue. And this graduate student, Neil Bellinson, was so generous. I mean, I think back on it, I'm like, it's so astounding. Every Saturday, he'd get up early to teach this kid for a couple of hours, number theory and geometry and various other things of that sort. And it allowed me to soar into regions of the mathematical universe that in any other context I would have never encountered. And it had a profound impact on me. In fact, a statement that he made to me, a statement that Neil Bellinson made to me, is the very first sentence in my book, Until the End of Time. And so you should do that. Maybe your teacher can write you a letter, or maybe there's a nearby university where you can knock on people's doors. And if you can find the right person, I was fantastically fortunate. But if you can find the right person, it can be life transforming. So Maria, I would encourage you to do your work, but follow the passion that your questions suggest that you have, and find somebody to nurture your talent and enthusiasm. Okay. Let's see. Mr. Castle DK asked, why is the top quark so much larger than other quarks? And larger, I think you mean by mass. And you're right, it is spectacularly larger, much heavier, much more massive. And nobody has an answer. We do not know why the particles, the fundamental particles of nature, have the masses that they do. And they span many orders of magnitude, right? I mean, the electron, roughly 1/2000th the mass of the proton. And then the top quark, roughly, 170 odd times the mass of a proton, right? Huge range, many factors of 10. But nobody has any explanation for why those fundamental particles have the masses that they do. That's one of the goals. Maybe unified theory would be able to do that. I don't know. That would be really cool, really spectacular. But no one has been able to do that yet. Now, look, having said that, we do understand how it is that quarks come together and yield the mass of a proton. Using quantum chromodynamics and lattice gauge theory, researchers, some of them are good friends of mine, have been able to calculate the mass of these combinations of particles. We don't know the masses. We don't have an explanation for the masses of the fundamental constituents, but when we group them together, we have been able to use our understanding of physics to predict the mass of the conglomerate, like a proton. So there is insight to the masses of some entities, but we do not have insight into the fundamental particles themselves, at least not as yet. So that's where things stand on that. Carbon Heart 000. I have great respect for you, Dr. Greene. I hope I can meet you in person one day. Thank you, Carbon Heart. If our paths were to cross someday, remind me of this message and this conversation, and I'd be more than happy to talk physics and the universe with you. Kenny Biddle, if the Big Bang happened in 0.3 seconds, 98% of the known universe, trillions of light years in every direction, so what about the speed of light limit? Kenny, I guess I get what you're after. You're after, how could the universe have grown so big in such a tiny fraction of a second if nothing can go faster than the speed of light? And Kenny, the issue there is to really understand deeply what the dictum that nothing can go faster than the speed of light, what does it mean? What it really means is that no entity, no object can pass through space at a speed